Tonight, we're going to talk about something that's been happening for billions of years. Something most people have no idea is even occurring right now. Our galaxy is being pulled through space by something massive, something hidden, something we can barely see. Right now, as you're watching this, we're moving at over 1 million miles per hour. And there's absolutely nothing we can do to stop it. For decades, astronomers knew something was out there because they could measure its effects, but they couldn't see what was causing it. An invisible force, powerful enough to drag thousands of galaxies across hundreds of millions of light years. And by the end of tonight, you're going to understand what's pulling us, why we can't escape it, and what this reveals about forces in the universe operating on scales that challenge everything we think we know about our place in the cosmos. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Right now, you're moving through space faster than you can possibly imagine. Not just because Earth is spinning on its axis, or because we're orbiting the Sun at 67,000 miles per hour. Not even because our entire solar system is racing around the center of the Milky Way at 500,000 miles per hour. No, there's another motion happening right now, one that most people don't know about. Our entire galaxy, all 400 billion stars, all the gas clouds, all the planets and solar systems, and everything we've ever known, is being pulled through space at 1.3 million miles per hour. That's nearly 372.8 miles per second, fast enough to cross the entire distance from Earth to the Sun in less than 4.5 minutes. And we're not moving randomly. We're being pulled in a very specific direction, toward a specific point in space, toward something astronomers call the Great Attractor. The discovery of this motion started with something that seems completely unrelated. The cosmic microwave background. This is the afterglow of the Big Bang itself, radiation that's been traveling through space for over 13.8 billion years. It's everywhere, filling all of space, and when astronomers first measured it carefully in the 1970s and 1980s, they expected it to look the same in all directions. After all, the Big Bang happened everywhere at once. There shouldn't be a preferred direction in the universe. But that's not what they found. When they measured the temperature of the cosmic microwave background across the entire sky, they discovered something strange. In one direction, the radiation is slightly hotter than average. In the opposite direction, it's slightly cooler. The difference is tiny, just a few thousandths of a degree, but it's definitely there. And there's only one thing that can cause this pattern: motion. When you move toward a source of radiation, the wavelengths get compressed, making it appear hotter and bluer. This is called blue shift. When you move away from a source, the wavelengths get stretched, making it appear cooler and redder. This is red shift. The pattern in the cosmic microwave background tells us we're moving. The Milky Way is moving through space relative to the cosmic microwave background at about 373 miles per second. That's over 1,300,000 miles per hour. But here's what makes this really strange. This motion isn't what we'd expect from just the expansion of the universe. The universe is expanding, yes, and that expansion carries galaxies apart. But what astronomers detected was something different, a peculiar velocity, a motion that's separate from the cosmic expansion, a motion caused by gravity. Something out there is pulling us. In the 1980s, a team of astronomers, led by Alan Dressler, started mapping the motions of galaxies in our cosmic neighborhood. They measured how fast galaxies were moving and in what directions. What they discovered was shocking. It wasn't just our galaxy that was being pulled. Thousands of galaxies, spanning hundreds of millions of light years, were all flowing in the same direction, all being pulled toward the same point in space. They called it the Great Attractor because that's exactly what it was doing, attracting, pulling thousands upon thousands of galaxies through space with its immense gravitational force. But here's the problem. When they pointed their telescopes at the region where the Great Attractor should be, they couldn't see it. Not clearly, anyway. And this wasn't because their telescopes weren't powerful enough. It was because of something called the zone of avoidance. The zone of avoidance is one of the most frustrating obstacles in astronomy. It's not a real physical zone, not a region of space that's actually different from anywhere else. It's simply our view, blocked by our own galaxy. The Milky Way is a disc-shaped galaxy, flat like a pancake, about 100,000 light-years across, but only about 1,000 light-years thick in most places. This disk is filled with stars, gas, and dust. Lots and lots of dust. And dust, despite being very diffuse by everyday standards, is incredibly effective at blocking light. The dust grains, typically smaller than a micrometer across, made of carbon and silicon compounds, absorb and scatter visible light. When you try to look through the plane of the Milky Way, through the densest part of the disk, the dust blocks most of the light from objects beyond. It's like trying to see through fog, except this fog is thousands of light-years thick and scattered across our entire galactic disk. The zone of avoidance covers about 20% of the sky, a band running along the plane of the Milky Way, where observations of distant galaxies are difficult or impossible using visible light. And unfortunately, the Great Attractor sits right in this zone. From our vantage point in the Milky Way's disk, about 26,000 light-years from the galactic center, the Great Attractor is in a direction that requires looking through thousands of light-years of our own galaxy's dust and gas. For decades, this made the Great Attractor one of the great mysteries of astronomy. Astronomers could measure its gravitational effects. They could see thousands of galaxies flowing toward it. They could calculate, roughly, how massive it must be and where it must be located, but they couldn't actually see what was there. This led to considerable speculation in the 1980s and early 1990s. Some astronomers proposed that the Great Attractor might be a supermassive black hole, far larger than any black hole in a galaxy's center. Others suggested it might be an enormous concentration of dark matter with very few visible galaxies. Some even wondered if it represented a fundamental flaw in our understanding of gravity or cosmology. What if gravity works differently on these enormous scales? What if there's some exotic physics happening that we don't understand? These weren't unreasonable questions. When you observe something unexpected, when the data doesn't match your expectations, you have to consider all possibilities, including the possibility that your fundamental assumptions are wrong. But, as better observations became available, as astronomers developed clever techniques for peering through the zone of avoidance, the true nature of the Great Attractor gradually became clear. The breakthrough came from using wavelengths of light other than visible light. Dust blocks visible light very effectively because the dust grains are roughly the same size as visible light's wavelength. This creates strong scattering and absorption, but dust is much less effective at blocking longer wavelength radiation. Infrared light, with wavelengths roughly 10 times longer than visible light, can penetrate dust clouds much more effectively. Radio waves, with even longer wavelengths, can pass through dust almost unimpeded. So, astronomers started using infrared telescopes and radio telescopes to map the zone of avoidance. What they found was galaxies, lots of galaxies, hidden behind the dust. These galaxies had been there all along, invisible to optical telescopes, but detectable at longer wavelengths. One of the key discoveries was the Norma Cluster, found in 1996 using infrared observations. This cluster sits almost exactly in the direction of the Great Attractor's gravitational pull, about 220 million light-years away. It's enormous, containing hundreds of large galaxies, with a total mass of tens of thousands of trillion solar masses. But it had been completely hidden from optical observations, blocked by Milky Way dust. Infrared observations revealed it for the first time, showing that the Great Attractor wasn't empty space or some exotic object. It was a massive concentration of galaxies, exactly what you'd expect based on the gravitational measurements. Subsequent observations using multiple wavelengths revealed more structure in the Great Attractor region. X-ray observations detected hot gas between galaxies in clusters. Gas heated to millions of degrees by the gravitational energy of the cluster. Radio observations mapped cold gas in galaxies, revealing star formation regions and the distribution of matter. Near-infrared surveys systematically mapped galaxies across the entire zone of avoidance, cataloging thousands of previously unknown galaxies. Each new observation added detail to the picture, revealing that the Great Attractor is not a single cluster, but a complex region containing multiple clusters, all part of a larger supercluster structure. The Norma Cluster is the largest and most massive, but it's surrounded by other clusters and groups, creating a concentration of mass that extends across tens of millions of light-years. Gravitational lensing studies added another layer of understanding. When light from distant galaxies passes near a massive structure like the Great Attractor, the gravity of that structure bends the light's path. This bending, predicted by Einstein's general relativity, can be measured and used to map the distribution of mass. Even dark matter, which doesn't emit or absorb light, can be detected this way because it still has mass and therefore curves space-time. Gravitational lensing studies of the Great Attractor region revealed that the mass is distributed in roughly the same pattern as the visible galaxies, but with much more total mass than the galaxies alone could account for. This confirmed what astronomers expected, that the Great Attractor, like all large structures, is dominated by dark matter. The visible galaxies mark where the matter is densest, but they represent only about 15% of the total mass. The rest is dark matter, forming an enormous halo that extends far beyond the visible galaxies and creates most of the gravitational pull. Understanding the structure of the Great Attractor required combining all these observations: optical, infrared, radio, X-ray, gravitational lensing, into a coherent picture. No single observation type could reveal everything. Each wavelength showed a different aspect of the structure. Optical observations, where they could penetrate the dust, showed the stars in galaxies. Infrared observations revealed galaxies hidden by dust and cool dust within those galaxies. Radio observations mapped cold gas and traced galactic structure. X-ray observations showed hot gas in clusters and around active galactic nuclei. Gravitational lensing mapped the total mass distribution, including dark matter. Combining all this data required sophisticated analysis, computer modeling, and careful comparison between different datasets. But the result was a detailed understanding of what the Great Attractor is and how it's structured. It's a supercluster scale concentration of matter. Multiple galaxy clusters embedded in an enormous dark matter halo, creating a gravitational well that pulls galaxies from hundreds of millions of light years away. The discovery process also highlighted an important point about astronomy. Our observations are always limited by our vantage point. We can only observe the universe from Earth, or from spacecraft relatively close to Earth. We can't move to a better location to get a clearer view. If something is hidden behind dust or gas, we have to find clever ways to observe it anyway, using different wavelengths, different techniques, different approaches. The zone of avoidance is a permanent feature of our observational situation. As long as we're in the Milky Way's disk, about 20% of the sky will be partially or completely blocked by dust. We can't eliminate this obstacle. We can only work around it by using infrared and radio observations that penetrate the dust. This means that even today, with our most advanced telescopes, there are almost certainly galaxies in the zone of avoidance that we haven't discovered yet. Hidden galaxies, blocked by dust, waiting to be revealed by future surveys. The zone of avoidance also affects other types of observations. When astronomers try to map the large-scale structure of the universe, the cosmic web of galaxies and clusters, they have to deal with a 20% gap in their data, the region where dust blocks their view. This makes it more difficult to understand the full three-dimensional structure of nearby space. It's like trying to do a jigsaw puzzle with 20% of the pieces missing. You can see the overall picture, but there are gaps, regions where you have to infer what's there based on surrounding pieces. Astronomers have developed statistical techniques to handle this, methods for filling in the gaps based on the structure they can see elsewhere. But it remains a challenge, a limitation imposed by our location within the Milky Way's dusty disk. Despite these challenges, the discovery of the Great Attractor stands as one of the great achievements of late 20th century astronomy. From detecting an anomalous motion in the 1970s and 1980s, to identifying the general location of the pull, to finally seeing the actual structure responsible in the 1990s and 2000s, it took decades of work by hundreds of astronomers. It required developing new observational techniques, building new telescopes capable of observing at infrared and radio wavelengths, analyzing data from multiple sources, and constructing theoretical models to explain the observations. But the effort paid off. What was once a complete mystery is now well understood. The Great Attractor is no longer mysterious or unexplained. It's a mapped, measured, understood structure incorporated into our models of the cosmic web and the large-scale structure of the universe. And the discovery process continues. Even though we understand the basic nature of the Great Attractor, there are still details being worked out. The exact mass distribution, the precise number of galaxies, the structure of the dark matter halo, the velocity field in the surrounding region, all of these are subjects of ongoing research. New surveys are being conducted, mapping more galaxies in the zone of avoidance, measuring their distances and velocities more precisely, building ever more detailed pictures of the structure. Computer simulations are being refined, incorporating better data about dark matter, dark energy, and the initial conditions of the universe, to predict how structures like the Great Attractor formed and how they'll evolve. And all of this work is part of the broader effort to understand the universe's large-scale structure, to map the cosmic web, to trace the flows of galaxies, to understand how gravity and expansion interact to shape the distribution of matter across billions of light years. The Great Attractor is one piece of this enormous puzzle, an important piece, because it's one of the largest nearby structures, one of the dominant sources of gravitational pull in our corner of the universe. But it's not unique. There are other great attractors, other massive concentrations of galaxies in other parts of the universe, all playing similar roles in their local regions. The Shapley Supercluster, beyond the Great Attractor, is even more massive, pulling both us and the Great Attractor toward it. The Perseus-Pisces Supercluster is another enormous structure about 250 million light-years away in a different direction. The Norma Cluster, about 300 million light-years distant, is one of the richest galaxy clusters known, containing thousands of galaxies. Each of these structures creates its own gravitational influence, pulls galaxies toward it, shapes the local flow pattern. And when you map all these structures and their gravitational effects, when you trace how galaxies are moving across hundreds of millions of light-years, you see the cosmic web emerge. Filaments of galaxies connecting massive clusters and superclusters, voids between the filaments, flows along the filaments toward the densest regions. It's a beautiful, complex pattern, created by gravity, acting on dark matter over billions of years, shaped by the initial conditions of the universe and modified by the ongoing expansion of space. The Great Attractor is one node in this web, one concentration point where multiple filaments meet, where matter has been flowing together for billions of years, where the density is high enough to create a gravitational influence that reaches across hundreds of millions of light-years. Understanding it helps us understand the web as a whole, the patterns of structure and motion that define the universe on its largest scales. It also helps us understand our own motion through space, why we're moving the way we are, what forces are acting on us. Before the discovery of the Great Attractor, astronomers knew we were moving, but didn't fully understand why. After its discovery, the picture became clearer. We're being pulled by nearby massive structures, the Virgo cluster, the Great Attractor, the Shapley Supercluster, all contributing to our peculiar velocity relative to the cosmic microwave background. This motion is not random or unexplained. It's the natural consequence of being embedded in the cosmic web, subject to the gravitational influence of all the mass around us. Every galaxy in the universe is experiencing similar influences, being pulled by nearby structures, flowing along filaments, participating in the large-scale motions that characterize the cosmic web. We're not unique in this regard. Our motion toward the Great Attractor is typical, representative of what happens throughout the universe, wherever there are galaxies and large-scale structures. The Great Attractor pulls us because it's massive and we're close enough to feel its pull. Other galaxies, in other parts of the universe, are being pulled by their own local massive structures, flowing toward their own great attractors. It's a universal phenomenon, gravity organizing matter, creating flows, building structure. And it's happening everywhere, all the time, as the universe evolves and structure continues to form. The Great Attractor is not just pulling us right now. It's been pulling us for billions of years since our galaxy first formed. Throughout Earth's entire history, throughout the evolution of life, throughout human civilization, we've been moving toward the Great Attractor. Ancient humans looked up at the stars, not knowing that those stars, and the Earth beneath their feet, were all rushing through space at over 1 million miles per hour. The builders of Stonehenge, tracking the sun and moon, had no idea they were passengers on a cosmic journey. Copernicus and Galileo, revolutionizing our understanding of the solar system, didn't know about the motion of the Milky Way itself. Even Einstein, whose general relativity provides the framework for understanding cosmic structure, didn't know about the Great Attractor or the flows of galaxies it causes. It's only in the last few decades, in the lifetime of people alive today, that we've discovered and understood these phenomena. This is one of the remarkable things about science. Each generation discovers new layers of reality, new phenomena that previous generations couldn't detect or understand. Our ancestors saw the stars and wondered what they were. Later generations discovered they were distant suns, and that our sun is just one star among billions. More recent generations discovered that stars are organized into galaxies, and galaxies into clusters. And now, just in the last few decades, we've discovered that galaxy clusters are organized into superclusters, that these structures are flowing through space, pulled by massive concentrations like the Great Attractor, all part of a cosmic web spanning billions of light years. Each discovery reveals that the universe is larger, more complex, more dynamic than we previously thought. And there's no reason to think we've reached the end of this process. Future generations will almost certainly discover new phenomena, new scales of structure, new aspects of the universe that we can't currently detect or imagine. The story of the Great Attractor is still being written. We've learned an enormous amount in the past few decades, but there's still more to discover, more detail to add, more connections to understand. And future astronomers, with better telescopes and better techniques, will see things we can't currently see, understand things we don't currently understand. The Great Attractor will remain a subject of study, a structure that helps us understand the universe for generations to come. But even now, with our current understanding, the Great Attractor tells us something profound. It tells us that we're part of something vast and ancient, a cosmic structure that's been evolving for billions of years. It tells us that motion and change are fundamental to the universe, that nothing is static or permanent. It tells us that gravity, one of the fundamental forces, shapes the cosmos on scales we can barely comprehend. And it tells us that we, small as we are, can understand these vast phenomena through observation, measurement, and reason. That's the real message of the Great Attractor. Not just that it exists, not just that it's pulling us, but that we figured it out. We discovered it, mapped it, understood it, incorporated it into our broader understanding of the universe. And we did this from a tiny planet orbiting an average star in an unremarkable galaxy, using nothing but our intelligence, our technology, and our determination to understand the cosmos we inhabit. The Great Attractor sits in a direction that's roughly along the plane of the Milky Way galaxy. Our own galaxy is a flat disk filled with stars, gas, and dust. When you try to look through that disk, all that material gets in the way. It's like trying to see across a foggy field. The stars and dust in our own galaxy block and absorb the light coming from behind them. So even though the Great Attractor is out there pulling us with incredible force, we can't get a clear view of it. Imagine knowing there's something massive in the basement of your house, something heavy enough that you can feel the floor tilting toward it. But when you go to look, the basement door is locked and you can't see through it. That's the situation astronomers found themselves in. They could measure the gravitational effects. They could see galaxies being pulled. They could calculate roughly how much mass was needed to create such a strong pull. But they couldn't actually see what was there. For years, this was one of the great mysteries of astronomy. What is the Great Attractor? How big is it? What's it made of? Astronomers had to get creative. They couldn't use visible light to look through the zone of avoidance. The dust blocks it too effectively. But dust doesn't block all types of light equally. Infrared radiation, which has longer wavelengths than visible light, can penetrate dust clouds much more effectively. X-rays and radio waves can also pass through. So, astronomers started using infrared telescopes, X-ray satellites, and radio observatories to peer through the zone of avoidance. What they found changed everything. In 1996, using infrared observations, astronomers discovered a massive cluster of galaxies called the Norma Cluster. This cluster sits right in the heart of the zone of avoidance, about 220 million light-years away from us. And it's enormous. The Norma Cluster contains hundreds of galaxies, maybe thousands. Many of them are giant elliptical galaxies, each one containing hundreds of billions of stars. The total mass of the Norma Cluster is at least 10,000 trillion times the mass of the Sun. That's 10 with 16 zeros after it. To put that in perspective, our entire solar system, including the Sun, all the planets, all the asteroids, everything, has a mass of about one solar mass. The Norma Cluster has the mass of 10,000 trillion suns. It's so massive that its gravity distorts space-time itself, bending the path of light that passes near it. This bending effect, called gravitational lensing, allows astronomers to map the cluster's mass even when they can't see all its galaxies directly. But even after discovering the Norma Cluster, something didn't quite add up. The Norma Cluster is massive, yes, massive enough to pull nearby galaxies toward it. But is it massive enough to pull our galaxy, which is 220 million light-years away, at over 1 million miles per hour? The math didn't quite work. The Norma Cluster alone couldn't explain all of the motion astronomers were observing. There had to be more mass there. More galaxies, more dark matter, more of something creating an even stronger gravitational pull. As telescopes improved and more observations were made with infrared, X-ray, and radio wavelengths, astronomers discovered that the Norma Cluster isn't alone. It's part of a larger structure, a supercluster of galaxies. This region of space, which includes the Norma Cluster and several other massive clusters, is now understood to be what astronomers originally called the Great Attractor. It's not a single object. It's a concentration of dozens of galaxy clusters, all packed into a relatively small region of space. The combined mass of all these clusters is staggering. Estimates suggest the Great Attractor region contains something like 100,000 trillion times the mass of the Sun. That's 1, followed by 17 zeros. A mass so large, it creates a gravitational well that pulls on everything around it for hundreds of millions of light-years. Our Milky Way is caught in this pull. We've been falling toward the Great Attractor for billions of years. But here's something fascinating. Even at over 1 million miles per hour, the distances involved are so vast that we're barely making any progress. At our current speed, it would still take us billions of years to actually reach the Great Attractor. In fact, we'll never reach it. And that's not because we'll find some way to escape. It's because there's something else going on, something even bigger that changes the entire picture. In 2014, a team of astronomers, led by Brent Tully, made a discovery that completely reshaped our understanding of the Great Attractor and our galaxy's place in the universe. Using more precise measurements of galaxy motions, they mapped out the flow of galaxies across a huge volume of space. What they found was that the Great Attractor isn't the end of the story. It's not the final destination. Instead, the Great Attractor itself is being pulled. There's something even more massive beyond it, something with an even stronger gravitational influence. That something is the Shapley Supercluster. The Shapley Supercluster sits about 650 million light-years away from us. That's 3 times farther than the Great Attractor, and it's absolutely enormous. The Shapley Supercluster contains thousands of galaxies organized into dozens of clusters. The total mass is estimated at around 10 million trillion times the mass of the Sun. That's 10, followed by 19 zeros. It's one of the most massive structures in the nearby universe. And its gravity is so powerful that it's not just pulling the Great Attractor. It's pulling thousands of galaxy clusters across hundreds of millions of light years. Our Milky Way, the Great Attractor, the Virgo cluster, where the massive galaxy M87 lives. All of us are flowing toward the Shapley Supercluster. We're all part of a massive cosmic current, a river of galaxies streaming through space under the gravitational influence of this enormous structure. This discovery led to an even bigger revelation. The team that mapped these galaxy flows realized that all these structures, the Milky Way, the Great Attractor, the Shapley Supercluster, and thousands of other galaxies, are all part of a single enormous structure. They called it Laniakea. The name comes from Hawaiian, meaning immeasurable heaven. And it's an appropriate name because Laniakea is almost impossible to comprehend in scale. Laniakea is a supercluster of superclusters. It contains approximately 100,000 galaxies spread across 520 million light-years. All of these galaxies are gravitationally connected, all flowing along the same massive structure in space. Laniakea has a center, a point toward which everything is flowing, and that center is roughly in the direction of the Great Attractor and the Shapley Supercluster. Think of it like a watershed on Earth. When rain falls on land, it flows downhill, following the contours of the landscape, eventually flowing into streams, then rivers, then finally into the ocean. All the water in a watershed is flowing toward the lowest point. Laniakea works the same way. But instead of water flowing downhill under Earth's gravity, it's galaxies flowing through space under the gravity of the most massive concentrations of matter. The Great Attractor is like a river in this watershed, a major flow of galaxies, all moving in the same direction. The Shapley Supercluster is like the ocean, the final basin where everything is flowing toward. And our Milky Way is like a drop of water somewhere in that river, being carried along by the current. We're not moving because we chose to. We're moving because space-time itself is curved by all this mass, and we're following that curvature. Just like a planet orbits a star because space-time is curved, our galaxy is moving toward the Great Attractor and the Shapley Supercluster because space-time is curved by their enormous mass. But what is creating all this mass? What makes the Great Attractor and the Shapley Supercluster so incredibly heavy? The answer is mostly dark matter. When you look at a galaxy cluster through a telescope, you see galaxies. Bright collections of stars that emit light we can detect. But those galaxies, all the stars and gas and planets they contain, only make up about 15% of the cluster's total mass. The other 85% is dark matter. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. The only way we know it exists is through its gravitational effects. When we measure how fast galaxies are moving in a cluster, they're moving too fast. If the cluster only contained the mass we can see, the galaxies would fly apart. The cluster wouldn't hold together, but they don't fly apart. Something is providing extra gravity, extra mass that we can't see. That something is dark matter. In a cluster like the Norma Cluster, there's vastly more dark matter than visible matter. The dark matter forms an enormous halo that extends far beyond where the visible galaxies are. This dark matter halo is what creates most of the gravitational pull. So, when we talk about the Great Attractor pulling us, what we really mean is that a huge concentration of dark matter is pulling us. The galaxies we can see are just tracers, markers that show us where the dark matter is. They're like foam on ocean waves. The foam shows you where the water is moving, but the foam itself isn't what's moving the water. The dark matter is the ocean. The galaxies are the foam. Computer simulations of the universe's structure confirm this. When cosmologists run simulations that include dark matter, they can reproduce the large-scale structure we observe. The cosmic web of galaxy filaments and clusters, the voids between them, the flows of galaxies toward massive structures like the Great Attractor. All of this emerges naturally from the gravitational influence of dark matter. The simulations show dark matter forming a cosmic scaffolding, a web-like structure where matter clumps along filaments and at the intersections of filaments. Visible matter, the gas that will form stars and galaxies, falls into this dark matter scaffolding. It collects in the densest regions where dark matter has already accumulated. Over billions of years, this process creates what we see today. Superclusters like Laniakea, with galaxy clusters like the Great Attractor and the Shapley Supercluster, marking the densest concentrations of both visible and dark matter. So the Great Attractor isn't really a single thing you can point to and say, there it is. It's a region of space where the cosmic web is particularly dense, where multiple filaments of dark matter intersect, creating a concentration of mass massive enough to pull thousands of galaxies toward it. The Norma Cluster and the other visible clusters in that region are just the parts we can see. The parts where enough visible matter has fallen into the dark matter halo to form galaxies and stars. Most of the Great Attractor's mass is invisible, dark matter that we can only detect through its gravitational effects. But even with all this understanding, even knowing that the Great Attractor is part of a larger structure flowing toward the Shapley Supercluster, there's still a fundamental question. What happens next? Where is all this heading? Are we going to crash into the Shapley Supercluster eventually? The answer is complicated, and it involves one of the most profound aspects of cosmology, the expansion of the universe. Space itself is expanding. This expansion, discovered by Edwin Hubble in 1929, means that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This isn't because the galaxies are moving through space. It's because the space between us and them is literally stretching. Now, locally, gravity can overcome this expansion. Our solar system isn't expanding. Earth isn't getting farther from the sun. Gravity holds the solar system together despite the expansion of space. Similarly, the Milky Way isn't expanding internally. Gravity holds it together. Even the local group, the collection of galaxies that includes the Milky Way and Andromeda, is held together by gravity. We're not flying apart. In fact, Andromeda is moving toward us, not away, because the gravitational attraction between the Milky Way and Andromeda is stronger than the expansion of space between us. But on larger scales, expansion wins. Distant galaxy clusters that aren't gravitationally bound to us are moving away, carried by the expansion of space. So what about the Great Attractor and the Shapley Supercluster? Are we gravitationally bound to them, or will expansion eventually carry us apart? The answer is, we're in between. We're close enough that we're being pulled toward them. The gravitational influence is real and measurable, but we're also far enough away that the expansion of space is working against that pull. As space expands, the distance between us and the Shapley Supercluster increases slightly every year. This expansion doesn't make the gravitational pull go away, but it does slow down our approach. Current measurements suggest that while we're moving toward the Great Attractor and the Shapley Supercluster, the expansion of space means we're doing so more slowly than we would if space wasn't expanding. And here's where it gets really interesting. The expansion of the universe isn't constant. It's accelerating. This acceleration, driven by something called dark energy, means that over time, the expansion is getting faster. Dark energy is even more mysterious than dark matter. It's a property of space itself, a kind of energy that causes space to expand faster and faster. We don't understand what dark energy is or why it exists, but we can measure its effects. And one of those effects is that the expansion of the universe is accelerating. As the expansion accelerates, it becomes harder and harder for gravity to pull distant structures together. Structures that are gravitationally bound today will remain bound. The Milky Way and Andromeda will eventually merge. The local group will stay together. Even galaxy clusters that are relatively nearby will remain gravitationally bound. But structures on the scale of superclusters, like Laniakea, are not tightly bound. The gravitational force holding them together is weaker than the expansion pulling them apart. Over billions and billions of years, as the expansion accelerates, Laniakea will be stretched apart. The flow of galaxies toward the Great Attractor will slow and eventually reverse. Galaxies will start moving away from each other as the expansion of space overwhelms the gravitational attraction. This means that the journey we're on, this flow toward the Great Attractor and the Shapley Supercluster, will never actually reach its destination. We'll keep moving in that direction for a while, but eventually, the expansion of space will stop us, then reverse our motion and carry us away. The Great Attractor will become unreachable, forever beyond our cosmic horizon. So in a sense, the title of this piece is both accurate and not. Yes, the Milky Way is heading towards something massive, the Great Attractor and the Shapley Supercluster beyond it. And yes, we can't stop it. We're caught in a cosmic current, flowing along with thousands of other galaxies. But we're not actually going to arrive. The expansion of the universe, driven by dark energy, will eventually win out over gravity. The Great Attractor will fade into the distance, moving away faster than light as space itself expands, until it crosses beyond the cosmic horizon and becomes forever unreachable. But that's billions of years in the future. For now, we're still moving toward it, still part of that cosmic flow. And there's something profound about that. Think about the scale of what's happening here. Our entire galaxy, with all its hundreds of billions of stars, all its planets and moons and asteroids, all the nebulae and black holes and everything we've ever observed, is just a single, tiny piece in a structure containing 100,000 galaxies. We're moving through space at over 1 million miles per hour, and we're barely even aware of it. The motion is so smooth, so consistent, that from our perspective, it's invisible. There's no cosmic wind rushing past us, no sense of acceleration or motion. Just the slow, inevitable drift through space-time, following the curvature created by dark matter we can't see, pulled by structures so massive they dwarf our galaxy, the way our galaxy dwarfs our solar system. And yet, for all that scale, for all that incomprehensible mass and distance and motion, we can understand it. We can measure it. We can map it. A species of primates on a small rocky planet orbiting an average star in one of those 100,000 galaxies has figured out that we're being pulled through space, has identified what's pulling us, has calculated how fast we're moving, and where we're headed. That's extraordinary. In the early 20th century, astronomers didn't even know that other galaxies existed. They thought the Milky Way was the entire universe. A century later, we've mapped structures spanning hundreds of millions of light years. We've discovered that our galaxy is part of a supercluster, that this supercluster is being pulled toward an even larger structure, that all of this is part of a cosmic web spanning the observable universe. And we've done all this from a single vantage point, a single planet orbiting a single star in one of those galaxies. The Great Attractor represents something important in astronomy. It's a reminder that the universe is vast, beyond our everyday comprehension. But it's not unknowable. For decades, the Great Attractor was a mystery, hidden behind the zone of avoidance, detectable only through its gravitational effect. But through persistence, through using different types of telescopes and different wavelengths of light, through building better instruments and developing better theories, astronomers figured it out. They mapped the invisible. They found the Norma Cluster. They discovered the Shapley Supercluster beyond it. They traced the flows of thousands of galaxies and mapped out the structure of Laniakea. And in doing so, they've given us a new perspective on our place in the cosmos. We're not stationary. We're not at the center of anything special. We're passengers on a journey we didn't choose, moving through space as part of a massive cosmic flow, pulled by gravity towards structures we can barely see. In a universe that's expanding and accelerating and carrying us toward an uncertain future. But what does this motion mean for us here on Earth? For our solar system? For our immediate cosmic future? The answer might surprise you. It means almost nothing. The motion of the Milky Way toward the Great Attractor has no effect on our daily lives, no effect on our solar system, no effect on anything in our immediate cosmic neighborhood. The sun will continue to shine. The planets will continue to orbit. Earth will continue to spin and orbit the sun. The seasons will continue to change. Life, if it continues to exist, will go on completely unaffected by the fact that we're racing through space at over 1 million miles per hour. This is because the motion is so smooth and so consistent. Everything in our local area of space is moving together. The sun, the planets, the entire solar system, all the nearby stars, they're all part of the Milky Way, and they're all being pulled toward the Great Attractor together. There's no relative motion between us and our neighbors. No cosmic wind, no turbulence, nothing that would tell us we're moving at all. It's like being on a train that's moving at constant velocity. Inside the train, you can't tell you're moving. You can walk around, pour a drink, toss a ball, all exactly the same as if the train was stationary. Only when you look out the window at the landscape rushing by do you realize you're in motion. For us in the Milky Way, looking at the cosmic microwave background is like looking out that window. It's the only way we know we're moving. But there is one future event that will be affected by all this cosmic motion, and it's something we've already mentioned briefly: the collision between the Milky Way and Andromeda. Andromeda, the nearest large galaxy to us, is currently about 2.5 million light-years away, and it's moving toward us at about 250,000 miles per hour. This motion is separate from the flow toward the Great Attractor. It's a local motion, caused by the gravitational attraction between the Milky Way and Andromeda. In about 4 billion years, give or take, Andromeda and the Milky Way will collide, or, more accurately, they'll merge. Galaxies don't really collide in the way solid objects do. The distances between stars are so vast that when two galaxies merge, the stars mostly pass by each other without hitting. But the gravitational forces reshape both galaxies, pulling them apart, stretching them into long tidal tails, eventually mixing their stars together into a new, larger galaxy. By the time this merger happens, the Great Attractor will be even farther away than it is now because of the expansion of space. The merger between the Milky Way and Andromeda is a local event, driven by local gravity, and it will happen regardless of what's happening on the larger cosmic scale. So, in a way, we're part of two different motions. We're part of the flow toward the Great Attractor, moving along with thousands of other galaxies in Laniakea. But we're also part of the local group, gravitationally bound to Andromeda and a few dozen smaller galaxies, on a collision course that will eventually create a new galaxy. Both of these motions are happening simultaneously. Both are driven by gravity, and neither one is something we can stop or even influence. We're passengers in a universe that's much larger and much more dynamic than our ancestors ever imagined. The Great Attractor also highlights something important about the nature of observation in astronomy. For a long time, we couldn't see the Great Attractor directly. It was hidden, blocked by our own galaxy's dust and gas. But we could measure its effects. We could see how it was pulling galaxies, how it was affecting their motions. And from those effects, we could infer that something massive was there. This is a common pattern in astronomy. We often can't observe things directly, but we can observe their effects and use those effects to understand what's there. Dark matter is another example. We can't see dark matter directly. It doesn't emit light or absorb light, but we can see its gravitational effects on galaxies, on galaxy clusters, on the bending of light passing near massive structures. And from those effects, we know dark matter exists. Black holes are similar. We can't see the black hole itself, the region inside the event horizon where nothing can escape. But we can see matter falling into the black hole, heating up as it spirals inward, emitting radiation before it crosses the event horizon. We can see stars orbiting the black hole, moving so fast that their motion reveals the presence of a massive dark object. The Great Attractor is part of this tradition. An invisible structure revealed through its effects on visible matter. And now, with better telescopes and better techniques, we can actually see parts of it. We can see the Norma Cluster and the other clusters in that region. But even now, most of its mass is invisible, dark matter that we can only detect through its gravitational influence. There's something humbling about all this. We live in a universe where most of the matter is invisible to us, where most of the energy is in a form we don't understand, dark energy, where we're being pulled through space by structures we can barely see, toward a destination we'll never reach, in a universe that's expanding faster and faster for reasons we can't fully explain. And yet, for all that mystery, for all that we don't know, we've learned an incredible amount. We've mapped the flow of galaxies across hundreds of millions of light years. We've discovered that our galaxy is part of a supercluster containing 100,000 galaxies. We've identified the structures that are pulling us, measured their masses, calculated their distances. We've done all this using physics, using mathematics, using careful observation and measurement. The Great Attractor isn't magic. It's not supernatural. It's gravity, the same force that makes apples fall from trees, operating on scales that are almost incomprehensibly vast. It's mass, ordinary and dark matter, concentrated in a region of space, curving space-time, causing galaxies to follow paths through that curved space-time. It's the same physics that governs the orbit of planets around stars, just operating on a scale that's a trillion times larger. And we can understand it. That's the real message here. The universe is vast. It's strange. It's filled with dark matter and dark energy and structures so large they take hundreds of millions of years to cross at the speed of light. But it's not incomprehensible. We can observe it, measure it, map it, understand it. A species that has only known about other galaxies for a century has managed to map the cosmic flows across superclusters, to identify the Great Attractor, to trace the influence of the Shapley Supercluster, to understand that we're part of something called Laniakea. That's an extraordinary achievement, and it's still ongoing. Right now, astronomers are making even better maps of galaxy flows. They're using new telescopes to peer deeper into the zone of avoidance, finding more galaxies in the region of the Great Attractor. They're measuring the motions of galaxies with greater precision, refining our understanding of how fast we're moving and exactly where we're headed. They're building better computer simulations that include dark matter and dark energy, trying to predict what the universe will look like billions of years from now. Every year, we understand a little bit more. The picture gets a little bit clearer. The Great Attractor becomes a little bit less mysterious. But even as we learn more, even as we map more of the cosmic web and trace more of the flows of galaxies, there's still a sense of wonder that comes from contemplating what we've discovered. We're moving through space at over 1 million miles per hour. We're being pulled by a concentration of mass so enormous it contains the equivalent of 100,000 trillion suns. We're part of a structure containing 100,000 galaxies, all flowing along invisible filaments of dark matter toward regions of even greater density. And there's nothing we can do about it. We can't stop this motion. We can't change our course. We're bound by gravity, by the curvature of space-time, by the distribution of matter across the universe. We're passengers on a cosmic journey that started billions of years ago and will continue for billions of years into the future. But being passengers doesn't mean being powerless. It doesn't mean being ignorant. We might not be able to change our path through the cosmos, but we can understand it. We can measure it. We can appreciate it. Let's step back for a moment and really think about what the Great Attractor represents in terms of pure mass and scale. To create a gravitational pull strong enough to drag our galaxy at over 1 million miles per hour from a distance of 220 million light-years requires an amount of mass that's difficult to conceptualize. We're talking about tens of thousands of galaxy clusters, each containing hundreds or thousands of galaxies, each galaxy containing hundreds of billions of stars. The Norma Cluster alone, just one part of the Great Attractor region, contains enough mass that if you could somehow gather it all into one place, it would outweigh our entire galaxy by a factor of tens of thousands. And that's just the visible matter. The dark matter halo, surrounding and permeating the Great Attractor region, is vastly more massive. When astronomers calculate the total mass needed to create the gravitational effects we observe, they find that about 85% of it must be dark matter. This dark matter doesn't clump into galaxies or stars. It forms an enormous, diffuse halo that extends for tens of millions of light-years in all directions. The galaxies we can see, the Norma Cluster and the others in that region, are embedded in this dark matter like raisins in a cake. They mark where the dark matter is densest, where enough visible matter has collected to form stars. But most of the dark matter halo is empty of stars, invisible except for its gravitational influence. And it's this dark matter that does most of the pulling. When we say the Great Attractor is pulling us, we really mean the dark matter halo is pulling us. The visible galaxies are just markers, helping us locate where all that invisible mass is concentrated. Understanding dark matter's role in the Great Attractor helps us understand one of the deepest mysteries in cosmology. How did structures like this form in the first place? Why is matter clumped into galaxies and clusters instead of being spread smoothly throughout space? The answer traces back to the very beginning of the universe. In the first moments after the Big Bang, matter was almost perfectly uniform. Almost, but not quite. There were tiny density fluctuations, regions where matter was slightly denser than average, and regions where it was slightly less dense. These fluctuations were incredibly small, variations of maybe 1 part in 100,000, but they were enough. Over time, gravity amplified these tiny differences. Regions that were slightly denser had slightly more gravity, which pulled in more matter from their surroundings, making them even denser. This created a runaway effect. Dense regions got denser and denser, while less dense regions lost matter and became voids. Dark matter played a crucial role in this process because it interacts only through gravity. Visible matter, the gas that would eventually form stars, can heat up, radiate energy, and lose momentum through collisions. This makes it more difficult for visible matter to clump together. Hot gas resists gravitational collapse because its thermal pressure pushes outward. But dark matter doesn't have this problem. It doesn't collide with other particles. It doesn't heat up or radiate energy. It only responds to gravity. So dark matter started clumping first, forming the initial structures in the universe. These dark matter structures then acted as gravitational wells, pulling in visible matter. The visible matter fell into these dark matter halos, cooled down, and eventually formed the first stars and galaxies. Over billions of years, small dark matter halos merged to form larger ones. Small galaxies merged to form larger galaxies. Galaxy groups merged to form clusters. Clusters merged to form superclusters. The Great Attractor represents one of the densest regions to emerge from this process. Multiple dark matter filaments intersect there, creating an area where gravity is particularly strong. Over billions of years, galaxies have been flowing along these filaments toward the Great Attractor, adding to its mass, making its gravitational pull even stronger. And the process continues today. Right now, galaxies are still flowing toward the Great Attractor, still adding to its mass. The structure is still growing, still evolving, but this growth is being opposed by the expansion of space. As space expands, it stretches the distances between structures, working against gravity's attempt to pull them together. For structures like the Great Attractor, which are massive enough to hold nearby galaxies, but not massive enough to overcome expansion on the largest scales, this creates a kind of equilibrium. Nearby galaxies continue to fall in, but distant galaxies, like those on the far side of Laniakea, are being pulled away by expansion. The result is that structures like the Great Attractor grow to a certain size and then stop growing as expansion overwhelms gravitational attraction at larger distances. This is part of why astronomers are so interested in mapping structures like the Great Attractor and Laniakea. These structures tell us about the balance between gravity and expansion, about the distribution of dark matter, about how the universe has evolved over billions of years. By measuring the motions of galaxies, by tracing the flows toward massive structures, astronomers can test their theories about how the universe works. And what they've found is remarkable. The flows match what we'd expect from our understanding of gravity and dark matter. The structures we observe match what computer simulations predict. The universe, for all its complexity, is behaving exactly the way our physics says it should. This gives us confidence that we really do understand what's happening, even when dealing with scales and phenomena far beyond everyday experience. The Great Attractor is also a reminder of how astronomy progresses. When it was first detected in the 1970s and 1980s, it was a complete mystery. Something was pulling galaxies, but no one knew what or where it was. Some astronomers speculated it might be a supermassive black hole. Others thought it might be a concentration of dark matter without many visible galaxies. Some even wondered if it might represent a flaw in our understanding of gravity. What if gravity doesn't work the same way on these enormous scales? What if we need new physics to explain what's happening? These were legitimate questions at the time. When you discover something completely unexpected, when the observations don't match what you thought you knew, you have to consider all possibilities. But as more data came in, as telescopes improved and observations became more precise, the truth emerged. The Great Attractor wasn't a single, exotic object. It wasn't a supermassive black hole or a flaw in physics. It was exactly what it appeared to be: a concentration of galaxy clusters embedded in an enormous dark matter halo, creating a strong gravitational pull. The mystery was solved not through revolutionary new physics, but through patient observation and measurement. By using different wavelengths of light to peer through the zone of avoidance, by mapping the motions of thousands of galaxies, by building better models of dark matter distribution, astronomers figured it out. And that's how science works. You observe something strange. You form hypotheses about what might explain it. You gather more data. You test your hypotheses against that data. Eventually, you converge on the correct explanation. It's not always dramatic. There's no single eureka moment where everything suddenly makes sense. Instead, it's a gradual process of accumulating evidence, refining models, testing predictions, until the picture becomes clear. The story of the Great Attractor follows this pattern perfectly. From mysterious anomaly to well-understood structure, mapped and measured and incorporated into our models of the universe. And in the process, we learn something profound about where we are and where we're going. The discovery of the flow toward the Great Attractor also changed how astronomers think about galaxy motions. Before this discovery, it was assumed that galaxies move in relatively simple ways. They orbit within their clusters due to gravity. They participate in the overall expansion of the universe. But large-scale flows, currents of galaxies streaming across hundreds of millions of light-years, weren't expected. The universe was thought to be more static on these scales, with galaxies essentially staying in their local neighborhoods. The Great Attractor showed this wasn't true. Galaxies are flowing on enormous scales, pulled by gravitational forces from distant structures. This realization led astronomers to start mapping these flows more carefully, measuring the motion of thousands of galaxies to understand where they're going and what's pulling them. And what they found was the cosmic web, the large-scale structure of the universe. Galaxies aren't scattered randomly through space. They're organized into filaments and walls, with vast voids between them. And all along these filaments, galaxies are flowing toward the densest regions, toward massive clusters and superclusters. The Great Attractor is one node in this web, one of the dense regions toward which galaxies flow. But there are others. The Shapley Supercluster is another node, even larger and more massive. And beyond that, there are other structures, other flows, a complex web of matter and motion stretching across the observable universe. Mapping this web has become one of the major projects of modern cosmology. Large survey telescopes measure the positions and velocities of millions of galaxies, building up a three-dimensional map of the universe's structure. These maps reveal the cosmic web in stunning detail, showing the filaments, the clusters, the voids, the flows, and they allow astronomers to test their theories. Computer simulations of the universe, starting from the conditions shortly after the Big Bang and evolving forward using the laws of physics, predict a cosmic web structure very similar to what we observe. The match between simulation and observation is remarkably good, giving us confidence that we understand how the universe evolved. The simulations show that the cosmic web is primarily a dark matter structure. Dark matter forms the scaffolding, the filaments and halos, where gravity is strongest. Visible matter falls into this scaffolding, forming galaxies and stars in the densest regions. So when we look at maps of the cosmic web, what we're really seeing is the distribution of dark matter, with galaxies marking where that dark matter is concentrated. The Great Attractor is visible on these maps as a node in the web, a region where multiple filaments converge, creating a concentration of dark matter massive enough to pull galaxies from enormous distances. These maps also show something else interesting. The voids, the empty regions between filaments, are truly empty. They contain very few galaxies, almost no visible matter, and presumably much less dark matter as well, since dark matter and visible matter follow the same large-scale distribution. The voids are regions where matter was initially slightly less dense than average, and over billions of years, that slight deficit was amplified by gravity. Matter flowed out of these regions toward the denser areas, leaving the voids behind. Some voids are hundreds of millions of light-years across, enormous bubbles of nearly empty space with filaments of galaxies surrounding them. Our galaxy, sitting in a filament, part of the flow toward the Great Attractor, is on the edge of one of these voids. If we look in certain directions, we can see the void, a region of space where galaxies are extremely rare. In other directions, we see the filament, the concentration of galaxies flowing toward the Great Attractor. This placement, on the edge of a filament near a void, is typical for galaxies like ours. Most galaxies in the universe are either in filaments or in clusters, the dense regions of the cosmic web. Very few galaxies are found in voids. And those that are tend to be small, dim, isolated galaxies, probably left behind when larger structures formed. Understanding our place in the cosmic web, understanding that we're part of a flow toward the Great Attractor, helps put our existence in context. We're not alone in space. We're part of a massive structure containing 100,000 galaxies, all connected by gravity, all flowing along the same large-scale pattern. And this structure, Laniakea, is just one of many superclusters filling the observable universe. When you look at a map of the universe on the largest scales, you see superclusters separated by voids, a pattern that repeats across billions of light-years. Each supercluster is like Laniakea, containing tens or hundreds of thousands of galaxies, organized into clusters and filaments, with galaxies flowing toward the densest regions. And all of this structure, all of these flows, are driven by gravity acting on dark matter. It's a beautiful example of how simple physical laws, gravity attracting mass, can create complex patterns when applied over enormous scales and vast stretches of time. The flow toward the Great Attractor is not just about our galaxy. It's about understanding how structure forms in the universe. how gravity shapes the distribution of matter, how we fit into the larger cosmic picture. Now, let's talk about the actual experience of this motion, or rather, the lack of experience. If you were, somehow, able to stand outside the Milky Way and watch it move through space, what would you see? At 1.3 million miles per hour, you might expect to see the galaxy blazing through space like a comet, leaving a trail behind it. But that's not what would happen. Space is nearly empty. The average density of matter in the universe is incredibly low, maybe a few hydrogen atoms per cubic meter in the space between galaxies. That's far more tenuous than the best vacuum we can create in laboratories on Earth. So, as the Milky Way moves through this nearly empty space, it doesn't experience any friction, any drag, any resistance. There's no cosmic wind pushing against it. No buildup of matter at its leading edge. It's not plowing through anything. It's simply moving, following its path through curved space-time pulled by gravity toward the Great Attractor. And because everything in our local region is moving together, all the nearby stars, all the gas clouds, everything in the Milky Way is moving at the same speed in the same direction, there's no relative motion. From our perspective here on Earth, we can't detect this motion at all, except by carefully measuring the cosmic microwave background. This is fundamentally different from motion on Earth. When you drive a car fast, you feel it. The wind rushes past. You feel the acceleration when you speed up or slow down. You see the landscape changing rapidly. But in space, motion at constant velocity is undetectable from the inside. This is one of the principles of relativity. There's no absolute reference frame, no preferred state of rest. All constant velocity motion is relative. You can only detect motion by comparing your velocity to something else. For us in the Milky Way, moving through space at 1.3 million miles per hour, there's nothing nearby to compare against. The other galaxies in our local neighborhood are all moving in roughly the same direction, all part of the same flow. So we can't see our motion relative to them. The only reference we have is the cosmic microwave background, the ancient radiation filling all of space. This radiation is isotropic, the same in all directions, when viewed from a reference frame at rest relative to the early universe. But when we measure it, we see a dipole pattern, hotter in one direction, cooler in the opposite direction. This dipole tells us we're moving relative to the early universe, moving through the sea of microwave radiation. And by measuring this dipole carefully, we can calculate our velocity. That's how astronomers discovered the flow toward the Great Attractor in the first place. They measured the cosmic microwave background, found the dipole, calculated our velocity, and realized we're moving much faster than the expansion of the universe alone would explain. Something was pulling us. But in our everyday lives, this motion is completely invisible and irrelevant. The sun rises and sets the same way it always has. The seasons change on their regular cycle. The stars maintain their patterns in the night sky. Everything is exactly as it would be if we were sitting still, because from our local perspective, we are sitting still. Everything around us is moving with us. This is why astronomy often deals with scales and phenomena that seem disconnected from everyday experience. The universe operates on timescales of billions of years and distance scales of millions of light years. On these scales, things happen that have no impact on our daily lives but are profound when we stop to think about them. We're part of a cosmic flow spanning 500 million light years, moving at speeds that would cross the distance from Earth to the Sun in minutes. And yet, We go about our lives completely unaware of it, because the motion is so smooth, so consistent, so perfectly shared by everything around us. It's only when we step back, when we measure carefully, when we think about the big picture, that we realize what's happening. And that realization, that understanding, is one of the gifts of astronomy. It allows us to see beyond our immediate surroundings, to understand our place in a universe that's vastly larger and more dynamic than everyday experience suggests. The Great Attractor is also interesting because it highlights the limitations of observation. Even with our best telescopes, even with observations across the entire electromagnetic spectrum, from radio waves to gamma rays, we still can't see most of what's out there. The dark matter that makes up most of the Great Attractor's mass is completely invisible. We can only detect it through its gravitational effects. Similarly, much of the visible matter in the Great Attractor region is hidden behind the zone of avoidance, blocked by dust and gas in our own galaxy. We've managed to peer through this zone using infrared and radio observations, but our view is still limited. There are almost certainly galaxies in the Great Attractor region that we haven't discovered yet, simply because they're hidden behind too much intervening material. This is a common challenge in astronomy. The universe is transparent to some types of light, but opaque to others. Visible light, the light our eyes can see, is blocked by dust, but infrared light can penetrate dust clouds. Radio waves can pass through even denser material. X-rays reveal hot gas that's invisible in other wavelengths. By combining observations at multiple wavelengths, astronomers can build up a more complete picture. But there are always limitations, always regions we can't observe directly, always matter we can only detect through its gravitational influence. The Great Attractor is a perfect example of this. Hidden partly behind our own galaxy, composed mostly of invisible dark matter, pulling us with a force we can measure but can't directly see. Astronomy requires working with incomplete information, inferring what's there from indirect evidence, building models that explain the observations even when we can't observe everything directly. And remarkably, this approach works. By measuring galaxy motions, by using gravitational lensing to map dark matter, by combining observations at multiple wavelengths, astronomers have constructed a detailed picture of the Great Attractor. They know roughly where it is, how massive it is, what it's made of, how it fits into the larger structure of Laniakea. All of this from observations made from a single location, our solar system, using light and other radiation that's traveled across millions of light years to reach us. It's an impressive achievement of inference and analysis. Let's also consider what the Great Attractor tells us about the future evolution of the universe. Right now, we're being pulled toward it. But as we discussed earlier, the expansion of space is working against this pull. And the expansion is accelerating, driven by dark energy. Over the next few billion years, the expansion will gradually overcome the gravitational attraction. The flow of galaxies toward the Great Attractor will slow down. Eventually, it will stop, and then it will reverse. Galaxies that are currently approaching the Great Attractor will start moving away from it, carried by the expansion of space. This process will take tens of billions of years, far longer than the current age of the universe. But it will happen. And when it does, the Great Attractor will become increasingly distant, eventually moving beyond the cosmic horizon, the distance beyond which we can no longer receive light or information. At that point, even if someone wanted to visit the Great Attractor, even traveling at the speed of light, they couldn't reach it. The space between us and it would be expanding faster than light could cross it. the Great Attractor would be forever unreachable, cut off from our observable universe. This is the ultimate fate of most structures in the universe. As dark energy drives accelerating expansion, the observable universe will shrink. Not in the sense that space itself shrinks, but in the sense that fewer and fewer structures will remain visible to us. Light from distant galaxies will be redshifted beyond detection. The space between us and them will be expanding too fast for new light to ever reach us. Eventually, in the far future, trillions of years from now, the only galaxies we'll be able to see will be those in our local group. The merged Milky Way Andromeda galaxy and the few dozen smaller galaxies gravitationally bound to us. Everything else, the Great Attractor, the Shapley Supercluster, the rest of Laniakea, the entire cosmic web, will have expanded beyond our horizon. Future astronomers, if any exist, will look out and see a much emptier universe. They'll see their own galaxy and a handful of neighbors, surrounded by darkness. They won't have access to the cosmic microwave background, which will be redshifted to undetectably long wavelengths. They won't be able to see distant galaxies or measure the expansion of the universe. Most of what we've learned about cosmology will be inaccessible to them. In a way, we're fortunate to exist at this particular time in cosmic history. Early enough that the universe is still full of observable structures. Late enough that we've developed the technology to study them, a few billion years earlier. And there wouldn't have been any astronomers because there wouldn't have been any complex life. A few trillion years later, and there wouldn't be much universe left to observe. The Great Attractor reminds us of this. It's a structure we can observe now, a flow we can measure, a phenomenon we can understand. But it won't always be accessible. The universe is changing, evolving, and our window for understanding it is limited. This brings us to an interesting philosophical point. What does it mean to say we're being pulled toward the Great Attractor if we'll never actually reach it? What does this motion signify if its ultimate effect is negligible? In one sense, the motion is meaningless. It doesn't affect our solar system, doesn't change life on Earth, doesn't alter our immediate cosmic environment. In billions of years, when expansion overcomes gravity, the motion will reverse, and we'll move away from the Great Attractor instead. The ultimate outcome is the same whether we're moving toward it or not. But in another sense, the motion is profoundly meaningful. It tells us about the structure of the universe. It reveals the distribution of dark matter. It shows us how gravity operates on the largest scales. It demonstrates that we're part of something much larger than ourselves, part of a cosmic web spanning the observable universe. The Great Attractor represents structure, organization, the clumping of matter under gravity's influence. And that structure is what makes galaxies possible, what makes stars possible, what makes planets and life possible. Without gravity pulling matter together, the universe would be perfectly uniform, just a thin soup of particles expanding forever, getting more and more diffuse, never forming anything interesting. It's gravity, acting over billions of years, amplifying tiny initial density fluctuations that creates all the structure we see. The Great Attractor is an extreme example of this structure, a region where gravity has pulled an enormous amount of matter together. And we're connected to it, part of its gravitational sphere of influence, flowing along the cosmic web toward it. That connection, that flow, that participation in cosmic structure is what gives our existence a context. We're not random, not isolated, not floating alone in an empty void. We're part of patterns that stretch across hundreds of millions of light years. Patterns created by the same physical laws that govern everything from falling apples to orbiting planets to the structure of the cosmos itself. Now, let's dig deeper into how astronomers actually measure these cosmic flows, because the methods are fascinating and tell us a lot about how astronomy works. The basic principle is simple. Measure how fast galaxies are moving, figure out what direction they're going, and map the overall pattern. But the execution is far from simple. First, you need to measure a galaxy's velocity. This is done using something called redshift. When a galaxy is moving away from us, the light from that galaxy is stretched, shifting toward longer, redder wavelengths. This is the Doppler effect, the same phenomenon that makes a siren sound higher-pitched when it's approaching and lower-pitched when it's moving away. With light, motion toward us causes blue shift, motion away causes redshift. By measuring how much a galaxy's light is shifted, astronomers can calculate its velocity. But there's a complication. The expansion of the universe also causes redshift. All distant galaxies are moving away from us because space itself is expanding. The farther away a galaxy is, the faster it's receding due to expansion. This expansion velocity is called the Hubble flow, after Edwin Hubble, who discovered it. To find a galaxy's peculiar velocity, the motion caused by gravity rather than expansion, you need to subtract the Hubble flow. You measure the total redshift, calculate how much of it is due to expansion based on the galaxy's distance, and what's left over is the peculiar velocity. But now you have another problem. How do you know the galaxy's distance? For nearby galaxies, within a few 100 million light-years, astronomers can use standard candles, objects of known luminosity. If you know how bright something really is, and you measure how bright it appears, you can calculate its distance. Certain types of variable stars, called Cepheids, are excellent standard candles. Their brightness varies in a regular pattern, and the period of variation is directly related to their true luminosity. Measure the period, you know the luminosity, measure the apparent brightness, calculate the distance. For more distant galaxies, beyond the range where individual Cepheids can be seen, astronomers use supernovae. Specifically, type Ia supernovae, which are thermonuclear explosions of white dwarf stars. These explosions have a fairly consistent peak brightness, making them useful as standard candles. By observing supernovae in distant galaxies, measuring their apparent brightness, and comparing it to their known true brightness, astronomers can determine distances. But this is painstaking work. You need to observe thousands of galaxies to map the flow pattern. You need accurate distances for each one. You need to measure their redshifts carefully. You need to account for measurement uncertainties. And you need to do all this across a huge volume of space to see the large-scale patterns. The teams that discovered the flow toward the Great Attractor in the 1980s spent years collecting data. They observed galaxy after galaxy, measured distances using Cepheid variables and other techniques, measured velocities using redshifts, and gradually built up a map of galaxy motions. What they found was that galaxies weren't moving randomly. There was a pattern, a coherent flow in a particular direction. And when they calculated what would be needed to create this flow, they realized there had to be an enormous concentration of mass in that direction, the Great Attractor. But measuring the flow was only the first step. Next came the challenge of actually observing the Great Attractor itself. As we've discussed, the zone of avoidance made this extremely difficult. Visible light observations showed very little, just the foreground stars and dust in our own galaxy. So astronomers turned to other wavelengths. Infrared observations, which can penetrate dust, revealed galaxies in the zone of avoidance that couldn't be seen in visible light. Radio observations detected gas and galaxies through the dust. X-ray observations found hot gas in galaxy clusters. By combining all these observations, astronomers gradually pieced together what was there. They found the Norma Cluster, along with several other massive clusters in that region. They mapped the distribution of galaxies, even those hidden behind our galaxy's disk. They used gravitational lensing, the bending of light by gravity, to map the dark matter distribution. And they discovered that the Great Attractor isn't just the Norma Cluster. It's an entire region of space containing multiple massive clusters, all part of a larger supercluster structure. This process of discovery illustrates something important about modern astronomy. It's not about single observations or single discoveries anymore. It's about combining data from multiple instruments, multiple wavelengths, multiple techniques, to build up a complete picture. No single observation told us everything about the Great Attractor. It was the combination of velocity measurements, infrared observations, X-ray data, radio observations, gravitational lensing studies, and computer simulations that revealed the full story. And this same approach is being used now to map the larger scale structure of the universe, to trace the flows of galaxies across billions of light years, to understand the cosmic web in detail. Large survey telescopes are measuring the positions and velocities of millions of galaxies. Space-based telescopes are providing high-resolution images free from atmospheric distortion. Supercomputers are running simulations that evolve billions of particles forward in time, predicting how structure should form and comparing these predictions to observations. The result is an increasingly detailed understanding of how the universe is structured and how that structure evolved. The discovery of Laniakea in 2014 was a milestone in this process. By carefully mapping the flows of galaxies across an enormous volume of space, astronomers defined the boundaries of our supercluster. They showed that the Great Attractor, rather than being the ultimate destination, is just one structure within a much larger flow pattern. They identified the Shapley Supercluster as an even more massive structure beyond the Great Attractor. And they gave us a new perspective on our place in the universe. We're not just in the Milky Way. We're in the local group. We're in the Virgo Supercluster. We're in Laniakea. Each level revealing that we're part of something larger, part of a hierarchy of structures extending to the largest scales the universe allows. This hierarchical structure, by the way, has a limit. Beyond the scale of superclusters like Laniakea, the expansion of the universe becomes dominant. Structures larger than superclusters aren't gravitationally bound. They can't hold themselves together against the expansion of space. So, superclusters represent the largest stable structures in the universe. Above that scale, the cosmic web is held together only by the ongoing flow of matter, not by gravitational binding. And as expansion accelerates, even these flows will be disrupted, leaving behind isolated superclusters that can no longer interact with each other. Understanding the Great Attractor has also helped resolve some puzzles about our motion through space. Before the discovery, astronomers knew we were moving relative to the cosmic microwave background, but they didn't fully understand why. The Virgo cluster, a large cluster of galaxies about 54 million light-years away, provides some gravitational pull, but it wasn't enough to explain our full velocity. The discovery of the Great Attractor provided the missing piece. It's massive enough and close enough to account for most of our peculiar velocity. And the discovery of the Shapley Supercluster beyond it explained why the Great Attractor itself is moving. Everything fits together into a coherent picture. We're being pulled by multiple structures at once, each contributing to our overall motion. The Virgo cluster pulls us. The Great Attractor pulls us. The Shapley Supercluster pulls both us and the Great Attractor. All of these pulls add up to produce our observed velocity of about 370 miles per second relative to the cosmic microwave background. And all of this happens because of gravity, acting on both visible and dark matter, shaping the flow of galaxies across hundreds of millions of light years. It's elegant, in a way. One simple force, gravity, operating according to well-understood laws, creates this complex pattern of motion and structure. The Great Attractor isn't mysterious anymore, isn't exotic or unexplainable. It's simply matter, a lot of matter, concentrated in a region of space, pulling on everything around it, according to the same laws that make apples fall and planets orbit stars. But the scale, the sheer immensity of it, is what makes it remarkable. Tens of thousands of galaxies, trillions upon trillions of stars, quadrillions of planets, all organized into a structure massive enough to pull our galaxy at over 1 million miles per hour from a distance of hundreds of millions of light years. And we figured all this out from our tiny vantage point, a small planet orbiting a small star in one of those galaxies, using mathematics and physics and careful observation. That's the real story of the Great Attractor. Not just that it exists, not just that it's pulling us, but that we discovered it, mapped it, understood it. From mystery to knowledge in a few decades of work. The Great Attractor also represents a broader truth about the universe. The universe is not static. It's dynamic, changing, evolving. Galaxies are moving, merging, being pulled by gravity, pushed apart by expansion. Structure is forming in some regions, dissolving in others. The cosmic web is not a frozen snapshot, it's an ongoing process. And we're participating in this process, whether we like it or not. We're not observers standing outside the universe, looking in. We're part of it, moving through it, subject to the same forces that affect everything else. Our galaxy is being pulled toward the Great Attractor right now, at this very moment. That motion is real, measurable, ongoing. It's not something that happened in the past or will happen in the future. It's happening continuously, every second of every day. Right now, as you read this, the Milky Way is hurtling through space at 1.3 million miles per hour. In the time it took you to read that sentence, we've traveled several thousand miles toward the Great Attractor. In the time it will take you to finish reading this entire script, assuming it takes an hour or two, we'll have traveled over 2 million miles. That's more than the distance from Earth to the Moon and back several times over. And you won't feel any of it, won't see any of it, because everything around you is moving with you. The motion is invisible, imperceptible, except through careful astronomical measurement. But it's real. This is what makes astronomy so fascinating. It reveals phenomena that are completely outside everyday experience. Motions and scales and timescales that have no parallel in our daily lives, yet are every bit as real as anything we can see and touch. The Great Attractor is pulling us. This is a fact, as well established as any fact in science. We've measured it, mapped it, understood the physics behind it. And there's nothing we can do about it, no way to resist or change it, because it's the natural consequence of mass and gravity and the structure of space-time. We're passengers in the universe, following paths determined by forces far beyond our control. But we're not helpless passengers, not ignorant ones. We understand where we're going and why. We've mapped the route, identified the forces driving us, predicted where we'll be in the future. And that understanding is a kind of power, even if we can't change the journey itself. Let's also talk about what the Great Attractor tells us about the nature of large-scale structure and how it formed. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were tiny fluctuations, quantum variations in density, but overall the universe was remarkably smooth. You could pick any volume of space, and it would contain almost exactly the same amount of matter as any other equal volume. But gravity amplified those tiny fluctuations. Regions that were slightly denser pulled in more matter, becoming denser still. Regions that were slightly less dense lost matter to their surroundings, becoming voids. This process is called gravitational instability, and it's responsible for all the structure we see in the universe today. Early on, small structures formed first. Dark matter halos, about 1 million times the mass of the Sun, just large enough for gravity to overcome the expansion of space and pull matter together. Visible matter, primarily hydrogen and helium gas, fell into these dark matter halos and cooled, eventually forming the first stars. These first stars were huge, hundreds of times more massive than the Sun, burning bright and dying young. When they exploded as supernovae, they enriched the surrounding gas with heavier elements, carbon, oxygen, iron, elements that didn't exist in the early universe. The next generation of stars formed from this enriched gas, and they were smaller, longer-lived, more like the stars we see today. Meanwhile, the dark matter halos were merging. Small halos combined to form larger ones. Galaxies merged to form larger galaxies. Groups of galaxies merged to form clusters. Clusters merged to form superclusters. This hierarchical growth continued over billions of years, building up larger and larger structures. The Great Attractor represents one outcome of this process. It's a region where multiple dark matter filaments intersect, where matter has been flowing together for billions of years, where the density is much higher than average. The galaxies we see in the Great Attractor region, the Norma Cluster and others, are the visible markers of this accumulation. They formed within the dark matter halos, in the densest regions where gas could cool and condense into stars. But most of the matter in the Great Attractor is dark matter, invisible but detectable through its gravitational pull. This dark matter halo extends far beyond the visible galaxies, creating the gravitational well that pulls in surrounding galaxies, including ours. Computer simulations can model this process in detail. They start with the initial conditions of the universe, the distribution of matter shortly after the Big Bang, tiny density fluctuations imprinted by quantum mechanics. They let gravity act on this matter for billions of simulated years, watching as structure forms. And what emerges from these simulations is remarkably similar to what we observe: a cosmic web of filaments and clusters with voids between them, flows of galaxies, along filaments toward dense regions, massive structures like the Great Attractor forming at the intersections of filaments. The match between simulations and observations is good enough that astronomers are confident they understand the basic process. Gravity, acting on dark matter and visible matter, creates the structure we see. The details might be complex, but the fundamental mechanism is simple. Matter attracts matter. Dense regions get denser. Structure grows hierarchically, from small to large. And the result, after billions of years, is a universe filled with galaxies organized into a cosmic web, with structures like the Great Attractor marking the densest regions. the Great Attractor didn't just appear suddenly. It's been growing for most of the age of the universe, accumulating mass as galaxies flow toward it, as smaller clusters merge into it, as dark matter continues to collect in its gravitational well. And it's still growing today, though that growth is being slowed by the expansion of space. Eventually, when expansion overcomes gravity completely, the growth will stop and begin to reverse. But for now, the Great Attractor is still an active structure, still pulling galaxies, still evolving. Understanding the Great Attractor also helps us understand our local cosmic environment in more detail. The Milky Way isn't just being pulled toward the Great Attractor. We're also part of a smaller scale structure, the Local Group, which includes Andromeda and about 50 other smaller galaxies. This local group is gravitationally bound. The galaxies in it will remain together even as the universe expands, even as distant structures like the Great Attractor eventually move beyond our reach. In about 4 billion years, the Milky Way and Andromeda will collide and merge. This merger is completely independent of the flow toward the Great Attractor. It's a local event, driven by the gravitational attraction between two massive galaxies that happen to be close enough for their mutual gravity to overcome expansion. When the merger happens, it will create a single, larger galaxy. This new galaxy will still be part of the flow toward the Great Attractor, still moving through space at roughly the same velocity. The merger won't change that. What it will change is the internal structure of the galaxy itself. The spiral structures of both the Milky Way and Andromeda will be disrupted. Stars will be scattered into new orbits. The result will likely be an elliptical galaxy, a vast swarm of stars with no organized disk structure. This merged galaxy, which astronomers sometimes call Milky Way, will be more massive than either parent galaxy. It will contain the combined mass of both, about 1 trillion stars, and it will continue drifting through space, part of the local group, part of Laniakea, being pulled by the Great Attractor and the Shapley Supercluster beyond. But by the time this merger happens, the Great Attractor will already be starting to fade from view. The expansion of space will be carrying it away, slowly but inexorably. In 10 billion years, in 20 billion years, the Great Attractor will be much farther away than it is now, receding faster and faster as dark energy drives accelerating expansion. Eventually, it will cross the cosmic horizon, the distance beyond which light can no longer reach us, and it will disappear completely from our observable universe. This is the fate of all distant structures. As expansion accelerates, more and more of the universe will become inaccessible. The observable universe, defined as the region from which light can reach us, will shrink. Not because space itself is shrinking, but because the expansion is carrying distant objects away so fast that their light can't keep up. Light from these objects, even light emitted today, will never reach us because the space between us and them is expanding faster than light can travel through it. This is one of the strange consequences of an accelerating expansion. There are galaxies we can see today whose light is reaching us now, but if they emit light tomorrow, that light will never reach us. We're seeing them at the last possible moment before they cross beyond our cosmic horizon forever. The Great Attractor will eventually suffer this fate, and when it does, future astronomers, if any exist, will have no way to know it ever existed. They won't be able to measure the flow toward it because it will be too far away to affect their motion measurably. They won't be able to observe it because it will be beyond the cosmic horizon. They won't even be able to detect its gravitational influence because gravity, like light, can't cross the cosmic horizon. Information can't travel faster than light, and if space is expanding faster than light, no information can cross that gap. So the Great Attractor, this massive structure that's pulling thousands of galaxies, including ours, will effectively cease to exist as far as future observers are concerned. It will have been erased from the observable universe by expansion. This is both humbling and thought-provoking. It reminds us that our view of the universe is contingent, dependent on when we happen to exist and where we happen to be. If we existed at a different time, we'd see a different universe. Earlier civilizations, if they'd had the technology, would have seen a younger universe, denser, with galaxies closer together. Later, civilizations will see an older universe, sparser, with fewer observable structures. We happen to exist at a time when the universe is still rich with observable structures, when we can see galaxies billions of light years away, when we can measure the cosmic microwave background and trace cosmic flows and understand the large-scale structure. This window won't remain open forever. In fact, it's already closing, very slowly, as expansion carries distant structures away. The Great Attractor represents part of this window. It's observable now, measurable now, understandable now. But that won't always be true. And that makes our observations of it, our understanding of it, even more valuable. We're documenting a structure that future civilizations, if they exist, might not be able to study. We're mapping flows that will eventually be disrupted by expansion. We're witnessing a phase of cosmic evolution that's transient, part of the ongoing changes that define the universe's history. Now let's think about the Great Attractor from a different angle. What would it be like to actually be in the Great Attractor region, in one of the galaxies of the Norma Cluster? If you could somehow travel there, what would you see? First, the journey itself would be extraordinary. At the speed of light, it would take 220 million years to reach the Great Attractor from here. You'd see the Milky Way receding behind you, shrinking to a point of light among billions of other points. You'd pass countless other galaxies along the way, each one a system of hundreds of billions of stars. You'd see the large-scale structure of the universe unfold, the filaments and voids, the cosmic web becoming apparent as you gained a wider perspective. And eventually, you'd approach the Great Attractor region. The density of galaxies would increase. Instead of seeing a few dozen galaxies in the sky, you'd see hundreds, thousands. The space between galaxies would be smaller, the gravitational interactions more frequent. If you could somehow stop and look around from a planet in one of the Norma Cluster galaxies, the night sky would be breathtaking. Dozens of galaxies would be visible to the naked eye, not just as faint smudges, but as clear structures, spiral arms, galactic cores, tidal tails from past interactions. Some galaxies would be close enough that you could see individual bright stars in them. The supergiants and hypergiants that shine brightly enough to be visible across millions of light years. The sky would never be truly dark, because there would always be the diffuse glow of countless galaxies providing background light. And if you had telescopes, if you could observe in detail, you'd see galaxies interacting everywhere. Tidal forces pulling streams of stars between galaxies. Mergers in progress. Galaxies slowly colliding and blending together over millions of years. New star formation triggered by these interactions. Bright blue regions where gas clouds are being compressed and igniting. The Great Attractor region is not a calm place. It's a region of intense activity, where galaxies are constantly interacting, merging, being reshaped by gravitational forces. But even there, on any individual planet, orbiting any individual star, life would probably be unaffected by all this drama. The distances between stars are still enormous, even in the densest galaxy clusters. Close encounters between stars are extremely rare. So even in the chaos of the Great Attractor, any planets that exist would orbit their stars peacefully, their orbits undisturbed, their conditions unchanged by the galactic dance happening around them. This is one of the peculiar features of the universe. On the largest scales, there's enormous motion and change. Galaxies flowing through space, merging, being reshaped. But on the scales of stars and planets, everything is calm and stable. The gulf between stellar scales and galactic scales is so vast that the two barely interact. So even in the heart of the Great Attractor, life, if it exists there, would experience the same stable, predictable environment that life on Earth experiences. Their sun would rise and set. Their seasons would change. Their planet would orbit reliably for billions of years. Only if they developed astronomy, if they looked up and measured and calculated, would they discover the enormous structures they're part of. This is true everywhere in the universe. The cosmic flows, the large-scale structure, the movements of galaxies, all of this is invisible to anyone who doesn't specifically study it. It's only through careful observation and analysis that we discover these phenomena. And that makes the achievement of astronomy even more impressive. We've discovered phenomena that are completely outside everyday experience, that require specialized instruments and sophisticated analysis to detect, that operate on scales almost incomprehensibly larger than human scales. And we've not just discovered them, we've understood them, explained them, incorporated them into a coherent picture of how the universe works. The Great Attractor is pulling us. This is a fact we discovered through decades of careful observation. And it's a fact that tells us something profound about our place in the cosmos. We're not the center of anything. We're not special in any cosmic sense. We're one galaxy among hundreds of billions, caught in a gravitational flow along with thousands of others, being pulled by structures we can barely see toward a destination we'll never reach. And yet, we figured this out. We mapped it, measured it, understood it. That's what makes us special. Not our location, not our size, not our importance to the universe. Our ability to understand the universe, to look at tiny variations in the cosmic microwave background and realize they mean we're moving. To measure the redshifts of thousands of galaxies and map their flows. To peer through the zone of avoidance using multiple wavelengths of light and discover what's hidden there. To build computer simulations that reproduce the structure we observe and tell us how it formed. A species of primates that evolved on a small rocky planet in an unremarkable part of an unremarkable galaxy has managed to map structures spanning hundreds of millions of light years and understand the primate forces that shape them. That's extraordinary. It's perhaps one of the most remarkable things in the universe, that the universe has produced creatures capable of understanding it. The atoms that make up our bodies were forged in stars. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all of it was created in stellar furnaces and scattered into space when those stars exploded. We're made of star stuff, as Carl Sagan famously said. But more than that, we're made of atoms that have been flowing through the cosmos for billions of years, part of the same large-scale structures we're now studying. The atoms in your body right now have traveled through space, been part of gas clouds, been pulled by the Great Attractor, participated in the cosmic flows we're describing. They're cosmically old, billions of years old, and they carry the history of the universe in their existence. And now, assembled into brains capable of thought, these atoms are contemplating their own cosmic journey. They're understanding the forces that move them through space, the structures they're part of, the flows they participate in. There's something profound and beautiful about that. The universe understanding itself through arrangements of matter that the universe itself created. This brings us back to the central theme. The Milky Way is heading towards something massive, the Great Attractor, and we can't stop it. We can't change our course through space. We can't resist the pull of gravity. We're passengers on a journey determined by forces that were set in motion billions of years ago when the universe first began to form structures. But we're conscious passengers, aware passengers, understanding passengers. We know where we're going and why. We've mapped the route, identified the forces, predicted the outcome. And that knowledge, that understanding, is itself remarkable. It doesn't change the journey, but it changes what the journey means. Instead of drifting through space, ignorant of the forces acting on us, we drift with knowledge, with understanding, with appreciation for the grand cosmic architecture we're part of. The Great Attractor, for all its mass and power, is just gravity at work. The same force that makes an apple fall to the ground, operating on scales a trillion times larger. The same mathematics that describes planetary orbits describes the motion of galaxies. The same physics that governs atoms governs the evolution of the cosmos. There's a beautiful unity to this. One set of laws, operating at all scales, creating all the phenomena we observe. From the smallest subatomic particles to the largest structures in the universe, it's all connected by the same physical principles. Understanding the Great Attractor is part of understanding this unity. It's seeing how gravity, one of the fundamental forces of nature, shapes the universe on the grandest scales. It's recognizing that the cosmos is not random or chaotic, but ordered, structured, following patterns that we can discover and comprehend. And it's appreciating that we, tiny as we are compared to these cosmic structures, are part of this order, subject to these same laws, connected to everything else through the fabric of space-time and the action of gravity. As we come to the end of this journey, let's remember what we've learned. The Milky Way is moving through space at 1.3 million miles per hour, pulled by a massive concentration of galaxies and dark matter called the Great Attractor, located about 220 million light-years away. This Great Attractor is part of an even larger structure, Laniakea, a supercluster containing about 100,000 galaxies, including ours. Beyond the Great Attractor lies the Shapley Supercluster, even more massive, pulling both us and the Great Attractor toward it. All of this is part of the cosmic web, the large-scale structure of the universe, created by gravity acting on dark matter over billions of years. The motion we're experiencing is real, measurable, ongoing, though imperceptible in our daily lives. We discovered it by carefully studying the cosmic microwave background and measuring the motion of thousands of galaxies. We mapped it by observing in multiple wavelengths of light, peering through the zone of avoidance to see what was hidden. We understood it by combining observations with theory, using our knowledge of gravity and dark matter to explain what we observe. And we've predicted its future, knowing that eventually the expansion of space will overcome this gravitational pull, carrying the Great Attractor beyond our cosmic horizon. The story of the Great Attractor is really a story about discovery, about using science to understand phenomena far beyond everyday experience. It's a story about how observation, measurement, theory, and simulation work together to reveal truths about the universe. And it's a story about our place in the cosmos, part of structures vastly larger than ourselves, moving through space according to laws we didn't create and can't change, but can understand. The Great Attractor is pulling us toward it right now. In the seconds it's taken you to read this far, we've traveled thousands of miles through space toward it. We're passengers on a cosmic journey that started billions of years ago and will continue for billions more. We can't stop it, can't change it, can't opt out of it, but we can understand it. We can appreciate it. We can marvel at it, and we can feel a sense of connection to something vast and ancient, a cosmic flow that's been underway since long before Earth existed and will continue long after everything we know has changed beyond recognition. The Milky Way is heading towards something massive, and now you know what it is, why it's happening, and what it means. Thanks for staying with me through this long journey across hundreds of millions of light years and billions of years of cosmic time. The Great Attractor is still out there, still pulling, still hidden partly behind our galaxy's disk, but no longer entirely mysterious. We've illuminated it with science, with observation, with understanding, and in doing so, we've learned something profound about the universe we inhabit and our small but significant place within it. We can look up at the night sky and know that every star we see is part of a galaxy that's moving, flowing along cosmic currents, pulled by invisible forces toward destinations determined by the large-scale structure of the universe. And we can marvel at the fact that we, tiny creatures on a small planet orbiting an average star, have figured all this out. The Great Attractor is still there, still pulling us, still drawing thousands of galaxies across hundreds of millions of light years. The Shapley Supercluster is still there, even more massive, pulling the Great Attractor and everything else in Laniakea. The cosmic web of dark matter is still there, channeling galaxies along filaments, creating the large-scale structure we observe. And we're still moving, still part of that flow, still on a journey we didn't choose. But now we know about it. Now we understand it. And that understanding, that knowledge, is something profound. It's a testament to human curiosity and ingenuity. It's a reminder that even when we're small, even when we're just passengers in a vast universe, we can still comprehend that universe. We can still map it, study it, understand it. The Milky Way is heading towards something massive. The Great Attractor, the Shapley Supercluster, structures so large they dwarf our galaxy. Structures containing so much mass they curve space-time and pull thousands of galaxies through space at speeds we can barely imagine. And we can't stop it. But we don't need to. Because this motion, this cosmic flow, is just part of how the universe works. It's gravity, operating on the largest scales. It's the consequence of matter, both visible and dark, distributed across space, creating structure, creating motion, creating the cosmic web we're all part of. And understanding that, appreciating that, is one of humanity's greatest achievements. We're small. Our planet is small. Our solar system is small. Even our galaxy is small compared to the structures we've discovered. But our understanding is not small. Our ability to observe and measure and calculate and comprehend is not small. We might be moving through space at over 1 million miles per hour, pulled by forces we can't control toward destinations we'll never reach. But we know about it. We understand it. And that makes all the difference. Thanks for staying with me through this journey across the cosmos. The Great Attractor is still out there, still pulling us, still hidden partly behind the zone of avoidance, but no longer completely mysterious. We've mapped it, measured it, understood its place in the larger cosmic structure, and in doing so, we've learned something profound about our place in the universe. We're not at the center. We're not stationary. We're not isolated. We're part of a vast, dynamic, ever-changing cosmos, moving through space, along currents we're only beginning to understand. And somehow, impossibly, from our tiny vantage point on a small rocky planet, we've managed to figure that out.